So for those of you who haven't glanced at it, our speaker tonight is Dr. Sarah Moran, and she's the director's postdoctoral fellow at the Lunar and Planetary Laboratory at the University of Arizona, where we get a lot of speakers from, I might want to add. We really love that institution. I certainly do. And she received her PhD in Earth and Planetary Sciences from Johns Hopkins University in Baltimore, which is actually where the Space Telescope Science Institute is based, if I remember correctly. And got her bachelor's in astrophysics and science and public policy at Barnard College at Columbia University in New York. And previously, she served as a space policy fellow at the National Academies of Sciences, Engineering, and Medicine. And she studies the atmospheres of extrasolar planets and planets in the outer solar system in her research. She uses a combination of atmospheric modeling, laboratory experiments, and observations from space telescopes to learn about worlds across the galaxy. She grew up in Kansas City, Missouri, and enjoys yoga, running, and science fiction, as I think most of our members do, and fantasy in her free time. And so without a further ado, tonight's speaker, Dr. Sarah Moran. Go ahead, Sarah.
Thank you so much for that introduction. Let's get the screen sharing here. So as mentioned in the intro, I did part of my, I did my PhD in Baltimore, basically on the campus of the Space Telescope Science Institute, which is why I got to be a big part of JWST, kind of as it was in its planning stages and ultimately launched. And I feel really lucky that that's how things worked out. I'm not totally sure how to answer questions while we're going. If you just stop and shout at me, I can try, and I'll do my best. That doesn't throw me usually, so we'll see. So this particular slide works better when I'm in person because you can physically see how tall I am, but I am 5'4", and this is to scale of just how big the mirror is on JWST. So Hubble is there too. That's what HST in silver is, just a little bit taller than me, but you can see I'm completely dwarfed by the James Webb Space Telescope. And that's one of the reasons that it is such an amazing instrument, is because it has all of this light gathering power that we can use to our advantage. You also notice that it's gold in this image, and that's the other reason, is that it's much more powerful as an infrared detector than Hubble is, for example. So pretty much everything I'm going to talk about today, not exclusively, but for the most part, involves spectroscopy. So as an astronomical society, hopefully you're maybe familiar with that, but that's really just this essence of taking light and dividing it into its constituent colors, into its constituent wavelengths. And by seeing what absorbs and what reflects and what scatters, we can then work back to figure out what the atmospheres of planets are made of, or if you're applying this to other things JWST is looking at, like galaxies and stars, you would learn things similarly. So this again goes into why JWST is so much more powerful than anything we've had before. This is breaking up all of those different wavelengths of light into their different regions. We have gamma rays on the shortest end, all the way to radio waves on the longest end. You can see this little region here that's highlighted is what Hubble covers. And so that includes the visible that we can see. It goes just a touch into ultraviolet wavelengths and just a touch into infrared wavelengths. And we've learned an enormous amount from Hubble. I never want people to walk away with the idea that I don't love Hubble, because I do. But you can see it's just covering this tiny little swath of the electromagnetic spectrum. And we used to have the Spitzer Space Telescope, which is what's highlighted here, which covered much longer wavelengths of infrared light. It wasn't quite as high resolution as the James Webb Space Telescope. It couldn't resolve things to the spectral level. Instead, we just call that photometry. So it got large bands of light. But it also went out of commission in about 2017, I think. And so we haven't had access to it, to these wavelengths of light, for a bit. And of course, here we have all of what JWST can see. And that includes a big portion of what Hubble can see, but in finer detail, which you'll see in a few slides, all the way out to the edges of what Spitzer could see. So these are a handful of solar system worlds. So from left to right here, we have Venus, Mars, Jupiter, Saturn, Titan, Neptune, and Pluto. And this is more or less what they would look like to our eyes. They've kind of enhanced in color in some ways to pull out contrast, but give or take, this is what it would look like if you could fly to each of these worlds and look at them. It's not what JWST sees at all. And so I'm sure, again, you know that the images we see from JWST are always interpreted. The raw images that come down from the telescope are generally in black and white because our eyes are not sensitive to infrared wavelengths. And there's an element of translation and actually a huge element of artistry and translating what those things look like to our eyes to make meaning of them. So the way I've structured this is sort of starting from close to home and then going further and further out. So we'll start with Mars, which is the closest thing that JWST can see. It can't actually turn around and look at Venus because it would be staring at the sun, which would ruin all the instruments, which would make us all very sad. So this image here on the left is a computer image of Mars, anything would see, but these two on the right are images from the James Webb Space Telescope. And you see these different gradations of color here. And so that's translating the infrared wavelengths at 2.1 microns, which is relatively near infrared, into colors that we can appreciate as humans. And the cool thing that comes out of here is this is Hellas Basin. You can see it's darker compared to this other bright spot. And this subsolar point that's labeled just means that's exactly where the sun is shining on the planet. And so this darkness here is actually because we're looking deeper. That basin is actually of lower relief. It's a valley. And therefore we're looking through more atmosphere to get there, which causes a temperature change, which is how this image is being created, is because it's actually cooler in that spot. Next, we're going to move on to Jupiter. This is not too different from what our eyes could see, but there are some features here that I want you to appreciate. So first of all, we see this beautiful ring of Jupiter, which is relatively difficult to see in visible light, but it pops out really strongly here in the infrared. And these blue regions at the poles are aurora that are being excited, and just like the gases that are being illuminated there. We also, of course, have the very familiar banded structure of Jupiter from different cloud layers. The great red spot looks a little bit less red in this image. And then out here is one of Jupiter's moons. So things are labeled here now to help you out a little bit. Don't know that there's anything that I haven't mentioned already, other than these kind of lights, sort of smudges that are emanating from the pole down here are actually light from the aurora being diffracted out that we can actually see. And now we're going to compare, so on the left here, what JWST sees in a little bit more enhanced color than that previous slide to what Hubble sees. And this blue material at the top is the only part of this Hubble image that isn't in visible light. This is actually ultraviolet light that's showing you those aurora really powerfully. And so the point that I want to make here is that these are giving us complementary sets of information. There's a lot of things that are the same, but there are details here that we're able to pull out from the near infrared that we couldn't see necessarily with Hubble alone. And similarly, like this aurora here that Hubble can tell us that JWST can't. And so these two observatories are really working together now. And so it's amazing to have them on sky at the same time. This is relatively recent. So this image that was taken of Jupiter was taken back in July 2022, but just a few weeks ago, after some more analysis of this image, we actually got some new science out of it. And so these different boxes that are highlighted here, these 3 different regions that the GTO team looked at, the Guaranteed Time Observations team. So those are the people who helped set up the telescope, helped sort of set the program for it. And as a result, they get special time to themselves to do kind of the science that they want to do. And so this image is taken about 10 hours apart from the top to the bottom. And so each of these little boxes that are highlighted, you can see that there's change that happened. You have this bright material here. It's now shifted over here. You have this wavefront kind of structure here. It's also moved on. And so from these images, the team was actually able to pull out wind speeds at different heights in Jupiter's atmosphere. You can visualize that this way. So here we're looking at height in the atmosphere on the y-axis going up and down, and then across how fast these things are moving. And so by looking at these different filters that picked up these different features, they can actually track how fast that material is moving. And so see that there are winds going at different speeds at different heights in the atmosphere, and they can calculate that from the shape of that shear, which I think is really cool. And you've always been able to do this on Jupiter with things like Hubble, but these particular wavelengths are too long to be accessed by Hubble. And so this was only able to be resolved with JWST to get this kind of information at these particular heights in Jupiter's atmosphere. This image is actually an engineering image. It was not done for science reasons at all, but I just really love it, and so I always like to show it. It hasn't been particularly cleaned up or anything. This is really just a raw image off the detectors from JWST. But the coolest thing here, I think, is this spot right here. So this is Jupiter's moon Europa. And Europa is completely covered in ice, which makes it very, very bright. It reflects a lot of light back. It's so bright here that this black spot is actually because we've completely saturated the camera. And so it's just getting no more information. And so it shows up as a black spot. And then you get these diffraction spikes again from the moon. But if you track over here, you see a dark spot on Jupiter itself. And that is actually the shadow of Europa on the planet, which I just think is the coolest thing, that we can image a shadow of another world with this infrared space telescope. And so even though this is engineering, was not done for science at all, we just get such incredible imagery back from this observatory. So speaking of Europa, this is what JWST sees when it looks directly at Europa, which is kind of fuzzy, but you have to remember this is a tiny, tiny little moon around a very, very bright object, Jupiter. And we still get this kind of incredible resolution. We can actually kind of pick out differences in color across the surface of the moon. And so this bright spot here is actually CO2 ice. And so if you go through different individual wavelengths of this instrument, you can make out regions where the ice is structured slightly differently because it's either made of crystalline form or it's complex, which means you've got sort of overlapping crystals that are not perfectly behaving together. And all of this is CO2 ice, which the team believes is actually not being delivered from afar. It's coming up from beneath the surface. So Europa is actually what's called an ocean world. It's completely covered in ice, but underneath that ice layer, there's a very, very thick, kilometers thick ocean. And so they think some of that material is actually able to reach the surface and then freeze out. And that's what we're seeing here. Now we're going to move to Saturn. So this is a very different image of Saturn than you're used to seeing probably. And that's because of the very particular wavelength that this image has been taken in. So it's this 323, which stands for 3.23 microns. And methane gas absorbs really, really strongly right about this wavelength. Saturn has a huge amount of methane in its atmosphere. And so when we look at the planet in this wavelength, all of the light is just being absorbed as soon as it hits that methane in the atmosphere, and we don't get anything back. Whereas if we look at the rings, which are primarily water ice, among other things, kind of rocky material, that's very, very bright because they're reflecting back the light very strongly at this wavelength, which is why the rings just pop out really beautifully here. And then all these other little dots around are actually moons. So now again, we're going to compare Hubble to JWST. And so the background image here is from Hubble, looking more familiarly like Saturn that we're used to. And then we're getting all of this fine detail out of JWST that we didn't necessarily have access to before, including this northern polar region on Saturn, where there's this hexagonal storm that actually forms and evolves over seasonal timescales. So I know the team is really excited to dig into this and see how things have changed since the end of the Cassini mission, which actually flew to the Saturn system. So this is Titan now, which is the largest moon of Saturn. It's an exciting place for a number of reasons. The biggest one, at least in my opinion, is because it has an atmosphere, a really, really thick atmosphere. It's actually thicker than that of Earth. It also has oceans or lakes on its surface at the poles. These lakes are not actually made of water, though. They're made of methane, that it's so cold on Titan that these are actually liquid. These things we think of as gases are liquid on the surface of Titan and make up the lakes. And so the team, when they imaged Titan with JWST, actually caught clouds forming. And again, these clouds are not made of water. They're made of things, again, that we think of as gases, ethane and methane. And so the These are two different filters looking at Titan. And so the haze here pops out really strongly. This cloud pops out really strongly. But if you go to slightly longer wavelengths, you can actually see through the atmosphere and start to make out the surface itself, where you see these dark materials that are sort of high plains, and then this sort of fuzzy region here, actually those lakes I was talking about. And so when the team saw this, they didn't necessarily expect to find a cloud. That they knew that clouds do form in Titan's atmosphere, but they didn't know they'd be lucky enough to see one. And so they saw this, and then they immediately contacted colleagues in Hawaii at the Keck telescope and said, can you please look for us at Titan and see if you can see anything? And so this JWST image was taken November 4th of last year. And then 2 days later, Keck was able to look at it, and they actually see the cloud moving on that time. So this cloud B here has shifted a little bit off the disk, and then cloud A is slightly moving more into view. So this is a team really working together with both ground and space-based telescopes to study these worlds. And before we leave Saturn, take a brief look at Enceladus, which is another ice ball that has a really thick ocean underneath the ice. This image is from the Cassini spacecraft when it flew through the system. So this is right up close. And you can see these jets at the South Pole here, and they're actually spewing that water from the subsurface out into space. And so when JWST took a look, this is what it saw. This very bright pixel is actually the moon itself. And then all of this material coming out is a plume of water that's just shooting into space. If we put that in context here, so again, this is the image. That bright pixel is the moon. And then here's the plume material. As it spews all of that out, it's actually putting all of that water into a giant ring around Saturn, because it's just spewing it out as it goes through its orbit. And so it's filling out this water torus, and it's called a torus just because it has this sort of donut shape. We actually think that this water that's coming out of Enceladus's subsurface is delivered to some of the other moons, including Titan. And that's how Titan actually gets some oxygen in its atmosphere from this water that's being just spewed out. Next up, going further out into the solar system, we have Uranus. This image just completely blew me away when I first saw it. I knew that Uranus had rings, maybe you did too, but I'd never seen them just so strongly in this high contrast here. They're just gorgeous. This very bright region here is what we call the polar hood of Uranus. And so it's this very thick haze that seems to form at the pole. And then over here, you probably have what's a bright cloud. Again, if we compare to Hubble here, which is now on the left, JWST on the right, we can see the ring, but we can just really pick out each individual ring structure with the increased power from JWST. This is that same image now, but we're kind of zooming out. And so each of these blue dots here are various moons of Uranus.
Sarah, this is Dave here. Again, forgive me for interrupting you, but are we seeing the shadow of the rings projected on the planet? Is that my imagination? The orientation looks right. On the right side?
Yeah.
Or is that just, go ahead.
I don't think so, because they would be very, with the way that the rings are oriented here, the light would be kind of directly down. Mm-hmm. If there was a shadow, you'd have to be sort of above the ring plane to look at it instead of at this sort of cross view that we're looking. I think actually what you're seeing here is just atmospheric structure.
Okay.
Yeah.
Thank you. Sorry to interrupt.
No, that's a good question though. And there are some amazing images of Saturn from the Cassini spacecraft where you do see shadows from the rings. But I think in this orientation, we wouldn't see that. Again, so as I was saying, all of these bright blue spots are moons. All of these sort of red fuzzy things in the background are actually galaxies. And that just kind of gives you a sense of scale here. You can zoom out even more and get some labels here on these different moons. We have Titania, Ariel, Miranda. If you want to talk more about some of these moons, I'd be happy to, but right now we don't have any better images of them than here. And then this is probably my favorite planet in the solar system, Neptune. And this is another image that, again, I was just completely flabbergasted when I saw. Again, we have these just gorgeous rings popping out that I had certainly never appreciated the rings of Neptune because I'd never seen them this way before. We also have these sort of very bright spots embedded within the rings here, in here. And we actually called these shepherd moons because they are moons and their gravity is actually helping shape the path of the rings and keeping them in the particular shape that they are. All of these bright spots on the surface, or not that Neptune has a surface, but on the what we can see as the planet of Neptune are cloud structures. And so these are storms that are just swirling around the planet.
Sarah, forgive me again. This is why nobody likes me, because I keep interrupting people. But that's a stunning image. I'm wondering what wavelengths are we looking at here? Is it covering the full range of everything JWST can? Go ahead, just tell us what wavelengths we're operating in. We're seeing it.
I don't actually know which specific wavelength off the top of my head. I know this is near cam.
Okay.
So that covers from like 2 microns out to about 4 microns in various band passes.
Okay.
I suspect this is a composite image of a couple different filters all in that range.
It's a stunning image. Thank you very much.
I agree. It's possibly my favorite that's come out so far. Certainly of the solar system worlds. So again, these are 2 images from Voyager and from Hubble. You can see that we got pretty good information from Hubble. This is from low Earth orbit, and then this is from when we actually flew by the planet with Voyager. And what's interesting here is that you can see these, again, these bright banding structures here from the Voyager image, so we could see these clouds, and then they kind of went away. You can maybe see a dark spot here that maybe has something to do with clouds here from Hubble. And then they just pop out really beautifully once we again have access to this further infrared wavelengths. So if we zoom out a little bit more, again, these background fuzzy red things are all galaxies. And this incredibly bright object here that is coming very, very close to saturating the detector is Neptune's moon Triton. Triton is this very funny moon. We think it actually might be a little bit more similar to something like Pluto versus a regular moon. It's suspected that it was actually an object that got captured in the gravitational well of Neptune. And so it just got stuck there as it was going through its orbit that it was originally around the sun. The reason we think that is because it's actually going backwards. So all the moons go with the same direction as the rotation of the planet, except for Triton, which goes the other way. Again, thinking that this object didn't originally exist with the Neptune system, it got captured later. It again is another one of these icy worlds that we think probably might have a subsurface ocean. And that ice layer on top is why it's just so incredibly reflective here. You can zoom out a little bit more. And so now some of these other moons are labeled for us. The other reason you can kind of tell that Triton is an oddball is because it's so much further from the planet as the rest of the moons, which tend to be a little bit closer because they probably formed all on the same disk, whereas this was a later addition. And then this image I just think is so cool because it makes me feel very, very small to look at, is that this is Neptune, sort of the very farthest reaches of our solar system, and all of these galaxies in the background. You get this, really beautiful arms on this one in particular. And so that's what we're looking out at as we move further into thinking about exoplanets, is that this is close to home, and we're going to go much, much farther in just a few minutes. So to me, the coolest part of exoplanets are because they essentially give you just a giant sandbox to play with. You say, how do planets form? And it kind of turns out anything you can dream up, the universe has made for us. And it's just kind of a matter of us putting all the pieces together to figure out why. In this image, this is an artist image, of course, we don't see these kind of disks. Everything that I show you pretty much from here on out, except for the very first, is going to be an artist image first, and then I'll show you the raw data, because we don't get these nice resolved disks because the objects we're looking at are much too far away. We just see point sources. So this is just to put it in a little bit of galactic context. So we're down here with the sun, and you can see in the early 2000s, we started to see a couple. Right about now, 2011, you see this huge explosion of planets, and that was actually the Kepler mission. which has found thousands and thousands of planets. At this point, as of, I think maybe a couple months ago, we actually hit 5,000 known exoplanets. So there are tons of them. Of those 5,000, we can actually characterize in a little bit more depth only a couple dozen. So although we know of all of these worlds, we only know just a very handful in any kind of detail. So this is the very best we're ever going to get with JWST in terms of actually imaging a planet. So this is a sort of newborn planet. It's just barely forming. So this is what the actual field of view looks like with the star. And then in these images, the star cartoon here is actually blocking out the starlight so we can image the planet next to it. So you see it in these various wavelengths of light, all here. And then in these particular two images, this is actually just a refraction effect. The planet doesn't have rings that we're making out here. That's just how the light is being scattered. But these are just broadband images in these different wavelengths of light. And we did learn some things about this particular planet from this, but it's not the main focus of the talk. This is really just to emphasize this is a particularly rare case where we can directly image an exoplanet. Most of the time, we're getting just spectroscopy out. And to introduce that, because it can be kind of hard to wrap your mind around, we're actually going to go back to Earth for just a second. So this is going in and out of an ozone band in the further infrared, around 9.5 microns. So of course, here we have Earth, and as we go in and out of this band where ozone absorbs, Earth seems like it gets bigger. And that's because all of that ozone gas is absorbing there and making it, in these particular wavelengths, look bigger to our eyes since we don't see ozone. The other kind of cool thing you see here is, of course, this is the moon in the background, which doesn't have an ozone layer or an atmosphere at all. And so as we go in and out of these different wavelengths of light, it appears to stay the same size. So that's really all we're doing when we do what's called exoplanet transmission spectroscopy, is looking for the change at particular wavelength bands to try to infer what the atmospheres of these planets are made of. And so this is a sort of perfect case. If we had infinite signal to noise, we would get these very just sort of sharp lines of where things absorb. The actual data a little bit messier than that. But in this particular image, what we're going in and out of here is this particular ozone band. So you can see it's a really, really strong atmospheric feature. It has this huge absorption right here. So now I'm going to tell you about WST-39b, which was sort of a run-of-the-mill exoplanet. It's called a hot Jupiter because it's about Jupiter's size, but very, very close to its parent star. So it means it's very, very hot. And it had some characterization from Hubble. We knew some things about it, but it was chosen as one of the first targets to be looked at with JWST. And therefore we know an enormous amount about it now that we didn't previously. So this was sort of the first thing that came out. This particular data was taken in July 2022, just maybe a week or maybe a week and a half into science operations of the telescope. I was lucky enough to be part of this team. And so I am actually a theorist or a modeler. I'm not the one who takes the data and makes it into something usable. I'm the one who makes that model in the background. This blue line is done by someone like me. And so I was sitting next to my friend who is a data person and just sort of waiting over his shoulder, hoping we would see something cool come out from the observations. And we were almost immediately rewarded. We got this huge spike right here, which is actually from carbon dioxide, which we had never detected on a planet outside the solar system before. So this was a huge moment for us. We were sitting outside, I think it was like a lunch break of some workshop that we were part of. And the two of us got very excited. And so people kind of started gathering around and around us as we just kind of kept pointing out, we did it. This, JWST is delivering on its promise. We detected carbon dioxide for the first time, as expected. It makes sense that on a planet this hot, you'd expect a lot of carbon dioxide. So we were really excited to see that. But you might notice that this model in the background that fits this carbon dioxide pretty well is not fitting this rise in wavelength right here. All of these little dots are the data, and they just really aren't hitting that blue line. And so relatively quickly after our excitement over this bump died down, we were like, well, what is this? That's not in the model. What could that be? And so we went through this whole process. It's this huge team of about 300 people from across the world thinking about what makes sense, what has an atmospheric feature here. And that was a mystery that took us maybe a week or 2 weeks to solve. So now I'm zooming out a little bit. So that's what I just showed you from where these arrows are. So you see our nice big spike from our carbon dioxide. You can see all of these other molecules in here. So we see water absorbing right here, here. We see a sodium feature spiking up right here. And this actually overlaps with Hubble. So we were able to stitch on and compare our observations to Hubble. And it agrees very nicely, but in much higher precision and detail. So that was exciting to see. And we ultimately were able to identify this mystery molecule as sulfur dioxide, which again, this is a new first. That's going to be kind of a theme for a while in exoplanet studies, that every time we make a new detection, we're going to get really excited. But sulfur dioxide in particular is exciting because it's actually a signature of something we call photochemistry. And so that's illustrated in this cartoon here. What's happening is starlight is coming in, breaking up water molecules. The oxygen and this hydrogen kind of float off this way. And then the other hydrogen goes and actually smashes into a hydrogen sulfide molecule. These processes kind of keep repeating as these different elements are bouncing around until ultimately you end up with a sulfur dioxide molecule. And so we had never seen evidence of photochemistry acting on a planet outside the solar system. So that was why we got so excited about this. And you can kind of compare this to something more familiar to you by thinking about ozone in Earth's atmosphere or even smog, which are also made by photochemistry, where starlight is breaking up gases and then they're reforming into these new products. So those are kind of the highlights from WST 39b. Now we're going into a planet, or maybe not a planet, depending who you ask, called VHS 1256b. And they're all kind of named in this very horrible phone number plus a letter way. And that's entirely based on the observatory that first characterized the star. And then that letter has to do with the planet. So this bit is the star from the stellar catalog, and then this B refers to the planet. Or in this case, it's really kind of on the threshold between a planet and a star. It's something we call a brown dwarf. So it's not quite hot enough to ignite fusion in its core, but it's really too big to be a proper planet. And so when you're getting images from, or when you're getting data from worlds like this, you're getting much, much higher precision than anything you can get when you're comparing starlight to a planet. This is a case where you're actually able to directly image the planet and then pull out a spectrum. So this is not a model. This is all beautiful, gorgeous data. So you can see here, we have, again, a lot of water, a lot of carbon monoxide here. This particular feature here is just kind of a cirrus stream because it looks exactly like the model does. But the kind of fun thing about VHS 1256b in particular is this region right here. There's a dip right here that is actually because of clouds in this planetary body's atmosphere. And again, this is really, really hot. It's almost 2000 degrees Fahrenheit, which means, again, water is not the thing that's making clouds. In this case, it's silicates. So things we think of as being rock on Earth are actually in the vapor phase and then just condensing out a little bit to where they make up this cloud layer that's absorbing at these wavelengths. And so this kind of silicate feature, as we call it, has been known for a long time for these brown dwarfs, these sort of intermediate objects between planets and stars. And we expect, because they have roughly similar composition, that we should also see things like this in planets. But because we didn't have access to wavelengths out here at high enough precision, we had never seen it in a planet before. That changed for the first time 2 weeks ago. So this is very brand new science. When we were able to measure this in a transiting planet, so again, a planet crossing in front of its star, on a planet called WST 17b. Again, this is an artist's image, kind of imagining what these cloud materials might look like. So again, now we're moving from those directly imaged planets to this sort of differential measurement where we're comparing the light from the planet and the star. And so you see the data here are these white dots. And this feature right here is the signature of those cloud particles. And we think the thing that fits best from the models are actually silicate oxides or quartz. Again, the thing that is rock on Earth is gaseous here. And we think that these are actually crystals. They compared things that are more crystalline to things that are more glassy. And the crystals fit better. So that's the signature we're seeing right here. And so this was also theorized for a long time, probably 10 to 15 years. This was expected. And so again, one of the first places we look, we find it with JWST. So I think I skipped, oh yeah. So now we're moving to kind of smaller planets here. This is a sub-Neptune, so-called because it's bigger than Earth, but smaller than Neptune in our own system. So we very creatively call them sub-Neptunes. This planet is very cold. It's called K218b, and it's actually about 10 to 30 degrees colder than Earth's average temperature, which means that it has a lot of methane in its atmosphere. And so that's seen here. All of these bumps here that are kind of guided by the model here are from absorption in the planet's atmosphere due to methane. There also might be some kind of hints of carbon dioxide here and here. Why this particular planet got a lot of press is because of this right here, this thing called dimethyl sulfide, which on Earth we think is only created through life, through plankton or other sort of methanogens on Earth that make this as a byproduct. So people got really excited, oh, this is kind of a sign of life. I am very much here to rain on this parade though. You'll notice here that these very strong bumps in the data that correspond to methane, you can pull out by eye, you can see those. These dimethyl sulfide features, you can't see, they just look kind of like lines, and that's because the data don't really show that they're there. This was a situation where the science team, I think, got a little overexcited, and so they put this particular molecule into their model, and they find that it kind of fits, and so they kind of went forward through it with this claim of a detection. But even they themselves call it they refer to it as a 1 sigma detection. So you may have heard that a 5 sigma is sort of like smoking gun. It's definitely there. In the exoplanet community, because we're looking at such small signatures, we tend to agree that 3 sigma is good enough. But this is barely a 1 sigma detection. So it's really, there's not evidence based on this particular data. This molecule is there. This planet is going to be looked at again with JWST, which will make all of these error bars even better. And so we can look again to see if this molecule maybe fits a little bit better than it currently does. But for now, I would not get my hopes up about this particular planet hosting life. It's very cool. Anyway, all this methane. And that's kind of illustrated here also. These white data are when Hubble looked at this planet. And Hubble looked at it, you see over here, 8 times to kind of beat down at the noise and make these error bars approximately the same size as all of this JWST data, where they looked once. Again, just illustrating how much more powerful JWST can be than Hubble. And when we only had Hubble data, we only had this region, people actually thought that this particular feature was due to water, because this is where water absorbs. It fits very nicely. You'll notice that these bands down here, where methane absorbs, overlap with the water. And so until we had all of this wider wavelength coverage, all of the many colors that JWST can see that Hubble cannot, we were confused and thought this was water until we could say, actually, no, wait, this is methane. And so I think a lot of planets, particularly where we thought that maybe this would be water, we actually need to revisit to make sure we weren't mistaken. We're going to go to even smaller planets now. We're finally in the realm of what are truly rocky worlds. So these are the TRAPPIST planets. They're probably the most famous rocky worlds outside the solar system. And that's because of the 7 planets in this system, 3 or 4 of them are in what's called the habitable zone, where if they were exactly like Earth, they would have liquid water on their surface, which we think then would make very good odds for them supporting life. And so there's a whole lot of interest in characterizing these particular worlds. And so the first ones that have come out so far are TRAPPIST-B and C, which means they're the 2 closest into their star. And instead of spectroscopy, at least initially, what's done here is actually just taking emission from the planet. And so how that works is as the planet crosses in front of the star and then behind the star, we measure the difference in the amount of light. So this line here is showing how bright the star and the planet are together. And then when the planet goes behind, we're just measuring how much light's coming off the star. And when it pops back out, again, we see that combined light. And so by measuring the amount of light coming here, what we're actually doing is taking the temperature of the planet. And so we can work out, based on how bright the combined light is, the temperature of the surface or the atmosphere, if there is one. And so we would expect it to be slightly cooler if there is an atmosphere. That's true of Earth too, because heat is being sent into the day side and then transported to the night side. That kind of modulates the overall temperature of the planet. Whereas if you just have one side being heated and then it goes into darkness, it becomes completely cold. And so the thing that we measured for these two innermost planets, which are not in the habitable zone, they're too close, is that they don't seem to have any strong amount of atmosphere. The amount of light that we detect is more consistent with them being bare rocks, and so just completely heated in the day and then cooling off at night. But there's, again, 5 more planets in the system for us to measure that are in the, some of which are in the habitable zone. So I don't think we have to give up hope just yet for the TRAPPIST-1 system. And then I will leave you with sort of a mystery. This is a place where JWST has shown us something very compelling but highly inconclusive. So this is GJ486b. It is what we call a super Earth. So it's about 1.3 times the size of Earth. It's very, very hot. It's 700 Kelvin, which is about 1,000 degrees Fahrenheit, more or less. And this is the thing we measured. So the data points here are in white. This is wavelength, so color on the x-axis, and then the amount of light that we are able to measure on the y-axis. And you can see that there's a whole lot of scatter here. They're not the nice, pretty, well-behaved lines where you can kind of almost with your hand draw a model that would fit. And that's because this object is so very tiny. And so this is a really tough signal to pull out. And so we measured this, and it's not quite flat, although it might kind of look that way. There's this sort of uptick here. And that slope is actually consistent with where water absorbs. And so our best fit atmospheric model, so I should say that I led this particular paper, which is why I'm going to start saying we. The best fit atmospheric model, if we assume the planet has an atmosphere, has a lot of water in it. And so that would be huge, right? This rocky planet not only has an atmosphere that we've detected for the first time outside the solar system, it has water. We didn't want to get too excited though, because, you know, putting our scientist hats on and be like, what are the other logical ways we could explain this data? And it turns out the star could be doing it. So this blue model here is if it were water, and this yellow model is if the planet had no atmosphere whatsoever, it was just a bare rock, but the star itself was imprinting water signals into our data. And that's because the planet, the star that this planet is orbiting is a really cool M dwarf. So it's much, much colder and smaller than the sun, which means it's much easier for there to be sort of transient water vapor in star spots on the star itself that we wouldn't necessarily know about when we do our data processing. And so that can manifest as imprinted water on our planetary signal. And you can see that these two different models almost completely align over the region where we have data from JWST. Luckily, you can see they get a bit different out here at these shorter, bluer wavelengths. And so we are already asking for more time on JWST with instruments that can measure these shorter wavelengths where these two models are different to see if we can't untangle this mystery and figure out which it is, whether it's just a star kind of messing with us, or whether it is in fact a signature of water in the atmosphere of a rocky planet. So that was sort of a whirlwind of just our first few months of planetary science with JWST. But just to kind of recap, we have seen the solar system in a whole new way, literally in a whole new light. We've already made some really interesting discoveries about how the winds are moving on these planets and about the chemistry of our own solar system planets. We also got our first detection of carbon dioxide on hot Jupiter, which we expected. We also saw sulfur dioxide on that same hot Jupiter, which was not expected to us at all, but very exciting, opening this new kind of regime of chemistry. We've seen rock clouds on a brown dwarf and an exoplanet, which was expected and was hoped for, but we have this whole new level of detail and precision that we didn't have, for example, with the Spitzer Space Telescope. And maybe, just maybe, we're inching our way toward discovering atmospheres on rocky Earth-like worlds. That hasn't happened conclusively yet, but I think that there's hope that there will be in the next few years, if not months, for this amazing telescope. So thank you all for your attention. If you haven't seen this image, this is from the launch of JWST. So after it got out of Earth's atmosphere and as it was kind of cruising its way toward its final position out past the moon, it got illuminated by the sun like this, which I think is just really beautiful. And the sort of amazing news is the launch went so perfectly that we get a huge more amount of science time than we thought we would. Sort of bare minimum for the mission to be successful was only going to be 5 years of it being operational in space. But because the launch went so perfectly, we actually have enough fuel to do corrections and whatnot that we expect it to last for about 20 years. So that's 15 more years of science than we expected to get, which I am personally very excited to see what we find. I'm happy to answer any questions that you might have. Thank you.
All right, thank you so much. Why don't you stop sharing your screen for a minute and put the lights on here. Great. All right. Funny thing is the first question that one of our members posted was, who's your favorite sci-fi author? That's the question I asked Sarah before we started the meeting tonight. And now that you've had another hour to think about it.
So this says movie, show, and/or book, so I will answer a few of them perhaps. In terms of show, I'm a big fan of The Expanse.
Yeah.
It balances a really nice, like sort of pulpy style with some very hard science, actually. So I'm a big Expanse fan. For book, I am currently reading a different novel by N.K. Jemisin, but her Broken Earth trilogy I thought was really amazing. And it kind of threads this line between sci-fi and fantasy, but I enjoyed it a lot.
Great, good answers. All right, how about you? Got questions?
Question. How many extrasolar planets has JWST looked at so far? Roughly.
So, I'm trying to picture this plot that I've seen before. I think it's on the order of like 40.
40.
And so some of those are probably repeats, like looking at the same planet a couple times. And so the data has not all been published yet. The data has been taken, but the teams are still like analyzing it and comparing it to models and trying to understand what it means. In terms of publications, I think that there are only maybe like 8 planets that have been published upon.
Is it on now? There
Now
it
it's
is.
on.
Okay. So, and we have over 5,000 solar planets. And so far, we've looked at approximately 40. Is that right?
Yeah, something like that.
Wow.
Well, good. We're going to need 20 years.
If we're lucky, yeah, we'll get 20.
So all of those 5,000 are not necessarily things we can look at with JWST. Like they're too far away, or they're too bright or too dim. So they don't necessarily translate to being something we can follow up on.
Do we have a rough idea how many we can look at with JWST?
I don't actually know off the top of my head. I would think it's something more in the hundreds.
Okay. That still will keep us busy for a while.
That will certainly keep us busy for a long time.
Very good. Okay, I'm not going to ask any more questions for now.
All right, well, you'll have your chance. A question came up, what programming language the models are written in?
So it depends on the modeler. I myself tend to use mostly Python, a little bit of Fortran. Those are probably the most popular, Fortran and Python. A couple people still
That's
use.
interesting. A really new language and a really old language.
Yeah, it turns out Fortran is just very fast. And so
Yes.
doing something very computationally expensive, it still makes sense to do Fortran and not Python.
Yeah, that's unexpected. That's cool. Go ahead, Dave, if you have more.
Yeah, I wanted to get a rough idea of the sizes of physical sizes of super Earths and super Jupiters. And because I would have liked sort of when we were looking at the images to have some sort of sense of scale as to how big these things actually are.
Mhm. So when we call things super Earths, we tend to mean up to just shy of twice the radius of Earth. So we don't have anything like that in our solar system to directly compare to. And then sub-Neptunes tend to be about twice the size of Earth, up to about 4 times the size of Earth, which is how big Neptune is. So kind of these middle ranges, the hot Jupiters are about the size of Jupiter. That's why we give them that name. It's really more about temperature, but in terms of size, they're like, 75% the size of Jupiter, up to like maybe 1.2 times the size of Jupiter.
I think I'm on now. So, and when do they cross over into the brown dwarf range, roughly?
It's actually a mass measurement, not a radius measurement necessarily. So once they hit about 13 Jupiter masses, that's when they can start doing deuterium fusion in their core, and that's we call them a brown dwarf.
Okay.
And they become a star when they hit that mass that they can actually burn regular hydrogen.
Okay, thank you.
Yeah.
Sydney is echoing a question I had when I was watching your presentation. You have a lot of nice data visualization in these slides. Is all of that coming from internally, scientists internally, or how does your data visualization team function? How much is internal? How much is external? How do you work with people who do that?
So most universities have some sort of in-house scientific artist. I think the vast majority of the ones I showed you here are actually from the Space Telescope Science Institute in Baltimore. They have a whole quite large team where that is their whole job, is to just take the science and make it into a beautiful artistic image that still illustrates the science. So I think most of them are Space Telescope, but most universities do have it. And so kind of the way it works is if you have a result that you think is a big enough deal that you kind of like to get more public attention from it, you go to Space Telescope and say, hey, we would like to do a press release. Can one of your team do some art for us? And that kind of kickstarts it. And it's a back and forth process. So at least for my GJ 486 paper, which was that planet that might have water in its atmosphere, or it might just be star spots. The initial image they sent us, I thought actually made it look too much like there was an atmosphere. And I was like, I don't want people to have the wrong idea. Can we make it more ambiguous? So it becomes a back and forth between the scientist and the artist.
Very cool. Thank you. Gert. Oh, go ahead.
Works?
Yes.
Within the next, whatever handful of years, this new generation of giant ground-based telescopes will be coming online. Compared to Hubble and JWST, what will be expectations or thoughts for quantum leap type discoveries for exoplanets coming from those?
So there's a whole lot of hope that those ground-based extremely large observatories will to detect biosignatures. So gases that are from things that we think only life can make. That's kind of just beyond the reach of JWST right now. The amounts of gases like that would be present or like the very edge of the signal to noise from JWST. So I personally would be kind of always skeptical of someone claiming that, whereas that will not be beyond ground-based very large telescopes. They will have the precision and accuracy that they should be able to pull those kind of signals out. So I think that is the real quantum leap there.
Steve Matthews, you raised your hand. I'm going to allow you to ask the question if you'd like. Steve, are you there? You're muted if you are.
Okay,
Yeah.
can you hear me?
Yeah. How you doing, Steve?
I'm doing great. I didn't know you were going to be here, Rich. I thought you were going to be out. At any rate,
I control the horizontal and the vertical.
okay.
Yeah.
This question may have already been answered, but does the Webb have the sensitivity to be able to detect biological signatures in the atmospheres of Earth-sized terrestrial planets that are in the habitable zone? Is that the limit of the resolution of the Webb? Or do we have to wait for these larger ground-based telescopes to be able to determine that?
So we do have to probably wait for these ground-based telescopes to do that. Like, that's kind of just beyond what JWST can do. If you got very lucky and it was sort of a very, very high signal noise target that was this habitable zone terrestrial planet, and you looked at it for maybe 100 hours with JWST, you might detect it. I think you'd be very hard pressed to convince your fellow scientists we needed to stare at one target for 100 hours to maybe make this detection, which is the other reason I think it's pretty unlikely. It'll be much faster to be done with ground-based telescopes.
When will we see these ground-based telescopes?
So they're supposed to start going online in the mid-2030s. So
Take good care of your health.
Yeah, we all take care of ourselves.
I don't know if it'll do me any good.
Stop it. All right. Thanks for the
Thank
question,
you.
Steve. Yeah. All right. Dave, go ahead.
I'm wondering, you just mentioned observing time. I can just see people at meetings like, fighting to the death for observing time. How much time do you guys get on your observations?
So there's like a whole process for how the observations get doled out. We actually just had on Wednesday another deadline of people proposing. And so the way this works is various science teams come up with an idea and say, okay, I want to look at this object for this long to do this science. And so they write all that down and they try to write a compelling enough case that, like, this is very important, we should do this. All those proposals go in to the Space Telescope Science Institute, who then make teams of other scientists, and we all read each other's proposals and then decide, okay, they made a really good case. You're right, that is important. We should do that. And so then that time gets awarded. And then in another case, people are like, well, that's not a very good use of time, so we'll chuck that one. And so it's this whole peer review process that gets scheduled out. So this last deadline that was due Wednesday, those observations won't actually start until 2025. So it's kind of decided well in advance.
Can you give us an idea of approximately how much time goes for each of these observations?
Yeah, so these little planets where you really need to keep staring at it to build up a lot of signal.
Yeah.
On the order of like 30 hours.
30 hours?
Yeah, you just keep staring.
Whoa.
That's a small one.
And the big ones?
The big ones you can usually do in more like 5 hours, 8 hours.
Wow, I had no idea it was that long.
Yeah, you just need to keep collecting all that light.
30 hours. Wow.
That's not, that's like astrophotography, Dave. 4 hours for
it actually
four
is
hours for a little bit of
astrophotography.
data, and 30 hours if you're going to spend the rest of your life, doing it right.
Wow.
It's not all that different. All right. Any other questions from the room here? Any of you guys? Deborah? Any? Okay. Let's see. We got a lot of thank yous from our audience and compliments on your love of The Expanse and the Broken Earth trilogy. Yeah, all right. So I guess that'll wrap it up. Thanks for putting up with our dysfunction from the start, and it looks like we recovered well from it. And
I did want to say one more thing before I go. Yeah,
please.
forgive me, Sarah, but I do want to plug our next month's speaker. And next month's speaker is Dr. Brian Day from NASA Ames. And he's going to be talking about lunar landing sites, both past and future, talking about landing sites for the Apollo missions, and then also talking about landing sites for Artemis. And I have a strong reason to believe we're going to find water at the landing sites. So that should keep you happy, Sarah, right?
I I suspect so too. I wouldn't take that bet.
All right. Well, we'll see. We'll start the pool. and
Okay,
we'll let you know.
and no pun intended.
Yeah. Yeah, right. No pun intended. All right. Well, take care. And thank you so much for your talk. It
Thank
was
you very
excellent.
much, Sarah. That was wonderful.
Thank you.
Good luck.
Thanks.